All right, welcome. Today we're going to tackle a really powerful technique for solving some integrals that honestly look pretty complex. We're going to break down how to use partial fractions to make integration not just possible, but, actually manageable. So let's just start with a problem. Take a look at this integral right out of a textbook. It looks pretty intimidating, right? You might try u substitution or some other methods, but you're not really going to get very far. But the method we're about to learn, that is the exact key that unlocks this kind of problem. So here's our game plan. First, we'll cover the core method itself. Then we're going to walk through some official textbook examples. After that, we'll practice with a few exercises just to build that muscle memory. And finally, we'll apply everything we've learned to some real exam questions. Okay, let's dive right into the method. The big idea behind partial fractions is really just a classic divide and conquer strategy. You take one difficult, kind of chunky fraction and you break it down into a sum of smaller, much simpler fractions that are way easier to integrate. But before you even start breaking anything down, there is one super critical question you have to ask yourself. Seriously, the answer to this determines your very first step, and it can save you a world of trouble. And that question is all about whether or not you have a proper fraction. In simple terms, all this means is that the highest power of x on the top of the fraction is smaller than the highest power of x on the bottom. That's it. This comparison right here is absolutely key. If your fraction is proper, like the one on the left, you can go straight to breaking it down. But, and this is a big but, if it's improper, where the degree on top is the same or bigger than the bottom, you have to do polynomial long division first. It is a non-negotiable step. So, you see what's happening here? It's really a two-step process. First comes the algebra, that's the decomposition, where you turn one fraction into several. Then, and only then, do you do the calculus, integrating each of those simple little pieces one by one. All right, enough theory. Let's get our hands dirty and move to the textbook to see how this works with some official examples. This is where it all starts to click. So our first one, example 8.13, is a classic. The denominator has two different kinds of factors, a simple linear one, x plus 1, and what we call an irreducible quadratic, x squared plus 3. That's just a fancy way of saying it's a quadratic that you can't factor any further using real numbers. Okay, pay close attention here because this setup is everything. Notice how the linear factor gets a simple constant a on top, but the irreducible quadratic factor, it needs a full linear term, bx plus c, on top. This is the rule that makes the whole thing work. From there, it's just a bit of algebra to find our constants. A is 1, b is -1, and c is 0. And after integrating those two simpler parts, we get our final answer. The first piece turns into a nice natural log, and the second one does too, after a quick little substitution. Okay, this next example, 8.14, introduces a new pattern, and you're going to see this one a lot. It's a repeated linear factor. See that little squared on the x minus 1? That requires a special setup. And here is that special setup. The rule is, for a repeated factor like x minus 1 squared, you've got to give each power its own fraction. So we need one term for x minus 1 to the first power and another for x minus 1 squared. This is the standard, crucial approach for any repeated factor you see. So we integrate each of those parts. Two become natural logs, and one is just a simple power rule integration, and that gives us this final expression right here. All right, we've seen how the pros do it in the textbook. Now it's time to reinforce that skill and build up some of our own confidence with a few problems straight from exercise 8E. We're going to move a little faster through these. The goal here is just to get good at recognizing the patterns we've just learned and see how they apply across some slightly different problems. First up, question 1A. You see those two distinct linear factors in the denominator, x and 2 minus x? Yeah, this is the classic, most straightforward setup you can get. It leads to a simple decomposition, and integrating gives us two natural log terms. Next up, 1e. And hey, look who it is, our old friend, the repeated linear factor. Just like in that worked example, the x minus 2 squared term needs that special setup. One fraction with x minus 2 on the bottom, and another with x minus 2 squared. Whoa, hold on a second. Before we jump into question 1F, stop. Before you even think about decomposing, look at the degrees. The top is x squared, and if you multiply out the bottom, it's also x squared. Since the degrees are equal,
It's an improper fraction. Our first step has to be long division. So after dividing, we get a whole number, 2, plus a new proper fraction. And it's this new, smaller fraction that we break down using our partial fraction method. Then we just integrate all 3 pieces, the 2 and the 2 new fractions, to get our final answer. Okay, so you might be wondering, what happens if this is a definite integral, with limits? Does the method change? Nope, not at all. The process is exactly the same. You just have one extra step at the very end where you evaluate the result.
So here in question 2a, we first decompose and integrate, just like always, but then we plug in that upper limit of 2, and we subtract whatever we get when we plug in the lower limit of 1. That gives us our final numerical value. Just take a second to look at how that flows. All right, let's get serious. It's time for the final, and you could argue the most important section, seeing how this crucial skill shows up on an actual exam. This is where we put it all together.
Okay, here it is, a classic exam question. Notice the factors on the bottom. 1 irreducible quadratic and 1 linear factor. Let's really take our time with this one and walk through it methodically, step by step.
And this just perfectly illustrates the whole process. We start with the correct setup for the decomposition. Then we do the algebra to find our constants a, b, and c. We rewrite our big, ugly integral as a sum of simpler ones, and look at step 4. We even have to split that first fraction again before we can integrate everything.
And just look at the answer. How cool is that? You get all these different functions popping out of that one integral. There's a natural log, there's an inverse tangent, and another natural log. It's a perfect example of just how powerful this method is.
All right, one last rapid-fire exam question just to make sure this is locked in. This one has that repeated factor x squared, right? Which you can just think of as x minus 0 squared. So the setup needs a term for x and a term for x squared, which leads us to this decomposition and our final answer.
Okay, so after all that, what are the big takeaways? If you're going to remember anything, make it these 4 points. 1. Always check if your fraction is proper first. 2. Your setup depends entirely on what kind of factors are in the denominator. 3. Remember, the whole goal is to make your life easier by breaking a hard problem into easy ones. And 4, this isn't just a clever trick. It's a fundamental tool for calculus that you're going to see again and again.
So we've unlocked a really powerful technique today for handling a whole class of integrals. It's a fantastic tool to have in your mathematical toolkit, which, really just leaves us with an exciting question to think about. What other elegant methods are out there, just waiting to simplify the seemingly impossible?